Hello again. This is the Pencrest High School AP Physics C video series. This is video 3B, work done. So we're going to look at some new ways to calculate the work done by an applied force. Last year we had a generic formula that said the work done by an applied force equals FAD cosine theta, where theta is the angle between the force and the displacement. You might recognize this formula, one vector times another vector times the cosine of the angle between them. You might recognize that as a dot product. So we can also say that the work done by an applied force equals the dot product of FA dot D. So the symbol, vector symbol D, of course, is the vector displacement. Sometimes this displacement is given the symbol R, vector R. If we consider that R is a generic position or displacement vector, if we expand the dot product, we would see that FA dot D equals FAX dx plus FAY dy plus FAZ dz. Each of those, of course, FAX, FAY, FAZ are the X, Y, and Z components of the applied force. dx, dy, dz are the X, Y, and Z components of the displacement. Conceivably, they could be presented to you in IJK format. We note that the dot product produces a scalar result, which is consistent with our concept that work and energy are not vectors. Again, this produces a scalar result, just a number of joules in terms of the work done by an applied force. Now, this formula is predicated on the assumption that the applied force magnitude is constant. So this will only work in the event that we're given an applied force that is not a function. If we consider the idea that a force could be variable over the position of an object, we have a graphical function here where the applied force is a function of x. This is a simple linear relationship, very similar to the ideal spring force, in which case we can determine the work done by the force by finding the area under this force versus position curve. In most cases, the work done by the force would be determined between two positions. So x initial and x final. You might be more comfortable using x naught and x to be consistent with the idea of initial and final positions in kinematics. Either way is fine as long as you know what you're talking about. So in this case, we have a linear relationship. In the event that we do not, we then can't use a simple formula. We can't even use the area under the curve because we have to integrate the function with respect to x. So we have a force as a function of position x, and we want to find how much work this force does between two positions. We have to integrate this function with respect to x. We are familiar with integrating functions with respect to t. Now we're going to integrate functions of x instead. So on your formula sheet, this work done formula is indicated as the integral of f dot dr. I'm going to clarify that a little bit, and I'm going to say that the work done by this force is the integral of f of x dx between xi and xf. So this is something of a new idea. It's called a definite integral. Definite integral determines the area under the curve between these two limits. So when we perform this type of integral between two limits, we do not need to add the constant of integration. So we don't need a plus c when we do this type of integration. So for example, we have a horizontal force, f of x equals 3x squared plus 2x minus 5. This force is in newtons and x is in meters. We want to know how much work the force does on this particle when the particle moves from x equals 3 meters to x equals 5 meters. So fairly straightforward problem. We set up the integral this way. Notice that we are integrating, there's my integral symbol. We're integrating the force function times dx here. And we're integrating from the initial position, which is we'll call the lower limit, to the final position, which is the upper limit. So from 3 to 5 meters. We integrate the function just as we did before. So 3x squared, we're going to take the x squared, raise it to the n plus 1, or the 1 higher power. We're going to carry the coefficient along with it, so we have 3x to the 1 more, 3x cubed over the 1 more, so 3x cubed over 3. We're then going to integrate the 2x. We carry the 2 along, 2x to the 1 more is 2x squared over the 1 more, and then minus, we have a constant 5 here, and that becomes 5x to the 1 more, which is 5x to the 1 when we integrate. So now we have a function here, 3x cubed over 3 plus 2x squared over 2 minus 5x. We're going to put that in square brackets, and then we're going to put the lower limit at the bottom and the upper limit at the top here. And now we're going to simplify the expression, and we're going to insert the upper limit for x, solve the function where x equals 5. We're going to insert the lower limit, solve the function for x equals 3, and then we're going to subtract the function evaluated at the lower limit from the function evaluated at the upper limit. So that's the nature of the definite integral. We're going to clean that function up a little bit. 3x cubed over 3 is just x cubed. 2x squared over 2 is x squared, and then minus 5x. We're going to evaluate that function from 3 to 5. Here is the function where x equals 5. Here is the function where x equals 3. Notice that I put them in parentheses. Evaluate this term, then subtract this term. And the answer is 104, which means this force, as the object moves from 3 to 5 meters, this force does 104 joules of work, or adds 104 joules of energy to the system. Okay? It is possible that the applied forces and displacements could be presented as functions in IJK format. So the functions do not need to be related other than that they act on the same object. We can represent the force function this way. F of x, or F sub x, is the x component of the force. F sub y is the y component. F sub z is the k component. So this fx and fy and fz could conceivably be functions of x, y, and z, right? So in other words, the force changes as x changes, the force changes differently. As y changes, the force changes differently as z changes. So they could each be individual functions. The position, of course, r is dxi plus dyj plus dzk. So the the displacement is going to be composed of changes in the x component and changes in the y component and changes in the z component. We could represent those as xi and xf, yi and yf, zi and zf. Initial and final positions along each of the three axes. So if we then consider each of the functions individually, we have the x function evaluated from xi to xf. We have the y force function evaluated from yi to yf. We have the z function evaluated from zi to zf. So we would perform those functions individually, integrate those functions individually, put in the limits, and then solve. You'll get a problem like this for your weekly WebAssign and also for your daily. We have three different functions. Here's the x function, the y function, and the z function. We evaluate each of those individually to find the work done between this initial position and this final position. So if we set it up, we notice that we integrate the x function from 3 to 5, and we find that the work done by the x component of the force is 200 joules. Similarly, if we evaluate the y function, 8yj, between 4 meters and negative 2 meters, we find that the y component of the force does negative work, negative 48 joules, in fact. And the z component of the force, 4z plus 5, between negative 4 and 3 meters in the z direction, will do 21 joules of work. Again, this is a scalar result, so these do not represent components of a vector, even though they do represent work done by the components of a vector. So it's important to make that distinction. When we get to the end, we don't represent this as a vector result. We just add the three work done amounts, and we get 173 joules in total. Okay? So those are some new ideas on how to calculate the work done. Again, in the event that you have a constant force, you can fall back on the simple dot product. In the event that force is shown graphically, if you can determine the area under the curve, use it. If you can't, if you have a complicated function, then you would need to execute an integral. Okay, and of course, if we have three-dimensional force functions indicated along with three-dimensional positions, we would then integrate each function individually between the limits that are presented and solve for the work done that way. Okay, so that's it for work done. And until next time, I will see you again soon.